The topic of this lesson are these things called diffraction gratings. Before we get there, I'm going to talk you through this little, I called it an analogy, kind of the background, why these things exist. So let's pretend good old days, we're sitting in our classroom and I gave you a measuring tape and I asked you to measure how far apart students were sitting from each other. Um, at the start of COVID, I literally had to do this walk around and make sure chairs weren't too close together before we switched to like cohorts and hybrid learning and all that good stuff. So let's say you've got the measuring tape and you're trying to figure out how far apart people are. The way I did it, one way to do it would be to measure from the center of one chair to the center of the next chair. But as I was doing it, what clicked into me is a chair is kind of wide. So when I measured from one to the other, it was easy to be off a little bit since I was measuring from a wide thing to another wide thing. As opposed to, I didn't do this, but let's say we were in the classroom and I asked you to measure the distance between the legs of your desk. Since the legs of the desk are kind of small, like a few centimeters across, like 2 or 3, you don't have to make as large of a judgment call when sort of locating where one leg is and where the other leg is. So you're a little bit more accurate when measuring from a leg of the desk to another leg of the desk than you might have been when measuring from one chair to another chair. The bottom line is, in science and physics, if we're measuring distances between narrow objects, generally speaking, we're more accurate than when we're measuring the distance between wide objects. Okay, file that away. Here's how that connects to wave optics. From last lesson, double slits. Double slits create this cool interference pattern. I'm going to describe them as evenly spaced smudges of light. So grab this off the internet. If we could do it, and when you see the data, this is kind of what it looks like. This kind of weird smudginess. There's light hitting kind of here. Oops. There's light hitting here, but then no light hitting right next to it. Then light hitting here, then no light hitting right next to it. That's the classic double slit pattern, these smudges of light that fade to dark and then come back. This top line here, if we had the light hit like a computer, like a light detector, and then graphed the brightness, the graph of brightness would kind of look like that. Kind of wide peaks that kind of fade as you get away from that central, that middle bright spot. So that'd be the brightest one. Oops. That would be the brightest one, and then they kind of fade to dark and then come back to bright, but that bright isn't as bright as the last one. Fade to dark and then come back. So it'd be that kind of almost like a dampened sine curve is sometimes what it's called. A sine curve that shrinks as we get away from that middle bright spot. Because they're kind of wide, actually it's all typed down here, because they're kind of wide, it's tricky to locate the exact position of a bright spot. If we're using a computer, you'd have to use some logic to try and tell the computer, okay, find the bright spot. So there'd be some programming involved in that. Maybe you say compare it to the spot beside you, and if your spot's a little bit brighter, then you know you're at the bright spot. Some sort of weird logic like that. Even if we're just using our eyeballs, it's tricky to locate the exact position of a bright spot because of that gradually brightening and gradually fading that goes on. It's a little bit easier to locate a dark spot. You just look for where there's no light, but even the dark spots aren't really narrow. So since they have some width, there's still some room for error in locating the dark spots. So bright spots are double slits are super cool. They make this awesome pattern that we can use to figure out wavelengths and different things, but there's room for error when using them. So a better device was created. Instead of a double slit, a diffraction grating has a whole bunch of slits marked into a surface. Often they just take an opaque piece of glass and scratch lines into it. So they would scratch a whole bunch of lines into it. So that your light, instead of going through 2 openings, is literally going through, well, it depends how close together they are and how wide your light is, but dozens of these narrow, crazy, tiny, narrow openings. The outcome is the superposition stretches out the dark spot or concentrates the bright spots into a more narrow position. So if we had a double slit with a particular D value, we'll get a pattern that kind of looks like this down here. If we had a diffraction grating with the same D value, there's a whole bunch of more lines, but they say they have the same D value as the double slit. The effect is the distance between those bright spots would be roughly the same, just the bright spots would be really, really narrow. If we graph these, instead of that kind of weird sine curve that tapered off, we get a graph that kind of looks like this. Localized, very bright spots. Because they're so localized, kind of like measuring the legs on the desk, if I had to measure from here, from there to there, pretend that's a straight line, if I had to measure the distance between consecutive bright spots, I can be a little bit more accurate. There's less room for error on those two ends, so I can get a more accurate number as to the positioning of those bright spots. And if I can get a more accurate number about those positions, then depending on what I'm doing with the math, maybe if I'm calculating wavelengths, let's say, I can get a more accurate value for the wavelength. So what I'm going to say moving forward is double slits produce these evenly spaced smudges of light. Gratings produce evenly spaced but narrow stripes of light. The very good news is we don't have to do another proof. It works out that the conditions are exactly the same as they were for the double slit. So for constructive interference, remember constructive interference meant the difference in path length was a multiple of lambda. We had two versions of it based on the angle. D sine of the angle is a multiple of lambda, or if we did that small angle identity, that dy over L is equal to a multiple of lambda. The condition for destructive interference was they had to be off by a half, and we had the exact same equations. The extra distance could be d sine x or dy over L. So equation-wise, gratings are going to work exactly the same, but usually in a question I'll never describe where the dark spots are. Because those dark spots are wide, it's hard to locate them. So in a grading question, I'll always talk about location of bright spots. One little wrinkle, so I want you to work through these two examples. There's one tiny wrinkle. In a grading question, you aren't given the D directly. In a double slit, D was the distance between the lines, or between the two openings. In a grading, D is going to be the distance between consecutive openings, but it's going to be communicated a little bit differently. Like in example 1, when you watch the video of the full solution, it's there. But basically, D is the distance in meters. So for this one, it was 1 centimeter. Often it's 1 centimeter. Every once in a while, you see like 1 millimeter or something. The D is 1 centimeter, so we're going to put that in meters. Oops, I said it and then I did it wrong. 1 centimeter is 0.01 meters. Then we're going to divide by the number of lines. So for example 1, our D value will be 0.01 meters divided by 500. Whatever we get by that division, that'll tell us the D value. So take a look at those two examples. There's a worksheet, that same worksheet. The first 4 questions were double slits. The next 2 are gratings, and one cool check-in related to a real-world application. And that's it for gratings. Email if you have any questions.